So hopefully you've had a chance to think about this transformation of v to this vector t of v. And I, by accident, wrote this the way that I normally write this. That was an accident. But the way that I usually write it is t of v. That's the way I should write it, I mean. But it's customary, just so that you are all aware, just to write t of v as tv, right? So it's the operator t applied to v. That's kind of the standard notation that most mathematicians use. I'm going to keep writing it t of v just to be perfectly clear that this is a function and where our input is v, our output is t of v, and so on. So that is, that's that. So quick correction there from last time, or quick, whatever, typo from last time. So I want you to think about what is this angle going to be here. So if I have some angle theta, how am I going to figure out what's the transformation corresponding to rotation of that angle in a counterclockwise manner? And hopefully you know that all we really need to figure out is the output vectors of 1, 0. So let's take our vector 1, 0, and let's take whatever our angle is, theta. And so we want to figure out what's this new output vector. And whatever that new output vector is, that's going to be the column of our matrix. Okay, so that's going to be the first column of our matrix. And then the second column of our matrix, okay, so the second column is going to be whatever our output vector is for the other basis vectors. So we're going to have 0, 1. And if we rotate by some angle theta, again, whatever that angle is, again, these are supposed to be the same length. But we need to figure out what is that output over there, that theta. And so that is going to be our job. Okay, so we need to figure out how this is going to work exactly. So this is the vector 1, 0. Okay, and 0, 1. So those are both, they're supposed to be, they are both supposed to be unit vectors. In other words, have length 1. So I'm not worried about the length, I'm just worried about where does that point end up. This is going to be some point, just to emphasize, this is going to be some point, our output vector is going to be some value along the circle centered at the origin of radius 1. Because if all we're doing is rotating, we're fixing the length, and then it's just going to move that vector. And so it's going to start at the origin, which is the center of the circle, and the tip of the vector is going to move along the circle in a counterclockwise manner. So this is all going to be rotation that's going to happen along a circle. But once we know that, I'm going to get rid of the circle because that kind of clouds the picture here. And so what I want to think about is we're going to start with where does the unit vector in the x direction go? So I hat or 1, 0 or however you want to say it. Where does that get moved to? What's the image of 1, 0? So we want to find the image of 1, 0. And so we're going to need a little bit of geometry here. We're going to have some angle, and we want to figure out what are the x and y values of those angles. And if we know that, then we're done. Because if we know that we're going to be able to have our vector. And so if you remember geometry, the x value is going to turn out to be cosine of theta. And the y value is going to turn out to be sine of theta. And we're done. We don't really need to do anything. There's not much for me to write to explain this, other than to know that if we start at the rightmost point of the unit circle, if we travel theta radians in a counterclockwise manner, okay, so if we travel theta radians in a counterclockwise manner, the new point that we get to has the coordinates cosine theta and sine theta. So when you project, this is what's called projecting this onto the x and y axis. When you think about the corresponding x and y values, this is cosine theta, and this is sine theta. Okay, and that's how we find that image of the vector 1, 0. So So that's the first, so let's just record that. So that's going to be the first column of our vector. So that's cosine theta, sine theta. So cosine was our x value, sine was our y value. The second thing that we need to do is figure out what is the output of the vector 0, 1. And what I want to do is I want to emphasize that this is actually going to be the same picture, just rotated 90 degrees. So this is going to be the same picture, just rotated 90 degrees, okay? So that is what we're going to have to figure out. And that means that the values are going to be similar. And so if I were to take this, and if you were to rotate so that this would be in line with the, if you were to rotate this so that this is in line with the, that didn't work out very well. Let's try that one more time. Take this so that you rotate it so that this is in line, whatever, with the unit vector in the x direction, I hat 1, 0, whatever, you would have the same values, right? You would have cosine and sine. But this is not the vector I hat, this is j hat. So you need to think about what are these values going to be. And so it turns out that the y value is really going to be cosine of theta. And the x value is going to be sine of theta, except that you have to think about the following. You know that this cosine value is going to be positive because it's a positive y value, but this sine of theta is going to be negative because theta, this is a negative x value, right? So this is to the left. So it's really not quite sine theta, but minus sine theta. And then other than that, it's exactly the same thing. So our x value is going to be minus sine theta. Our y value is going to be cosine of theta. And we're done. Our A, I shouldn't have written A here. Our A is a 2 by 2 matrix. And the second column is going to be minus sine theta over cosine theta. And it turns out that if I take any vector v and I multiply this vector v on the left by a, that's going to correspond to rotation of v by theta radians in the counterclockwise direction. Okay, and so that's exactly in the in the counterclockwise direction. This is a transformation that gets used over and over and over and over, and was actually this is a little silly, but this transformation was actually implicitly used when I rotated this, right? The computer knew where to send this vector based on this actual transformation that we found. This is a huge component of computer graphics. If you want to rotate a picture, you apply this transformation. Pictures are two-dimensional, so we're really taking maps of R2 and sending it to R2, and this is really useful for computers to know exactly where each pixel gets sent to after a transformation is applied. Okay, so there's a lot of computer graphics that are floating around in these linear transformations, and we'll get into, there's one other computer graphics example I want to talk about. The last thing I want to talk about with this video is I just want to think about what if, so just to tie our two last examples together, what if theta is pi over 2? What if we're talking about a rotation by 90 degrees or by pi over 2 radians in the counterclockwise manner? Well, if that's the case, then what's A? Theta is going to be pi over 2. So this is going to be cosine of pi over 2, sine of pi over 2, negative sine of pi over 2, and cosine of pi over 2. Sorry to squeeze that in there. And cosine of pi over 2 is 0. Sine of pi over 2 is 1. And we really do end up with that matrix 0, -1, 1, 0 that we were talking about 2 examples back, right? Here's our matrix, 0, -1, 1, 0, right? So that's really a special case of what we were just talking about for this translation, for this rotation matrix.